Hello everyone, welcome back to gradient and directional derivatives. And first of all, again, it is about the gradient. The gradient, it is a vector formed by the partial derivatives. Certainly for function of two variables, it is a two-dimensional vector. For function of three variables, the gradient, it is a three-dimensional vector. And also, we know the directional derivative can be calculated using the gradient dot with the unit vector. The unit vector, it is the direction. And in general, mostly we consider the case in the for function of two variables. So which would represent a surface. And this is a bigger part. I say at any point on a smooth surface, okay, there are different derivatives in different directions. As I mentioned in the other video, consider you are climbing a mountain. The surface of the mountain, it is the surface we are talking about. So at a single point, you could go up, you could go down, and then you could go any directions. There are different rates of change. So that is the thing. At a single point on a smooth curve, there are many different derivatives in different directions. That is the so-called directional derivative. And also, if you understand that there are many directional derivatives, another question we want to answer is mathematically the maximum. What is the maximum rate of change, maximum value of the derivative, and in which direction it may occur? So the gradient answers both. The gradient says in the direction of the gradient, the function has the maximum rate of change. And also the maximum rate of change, it is just the magnitude of the gradient. Last time, I think we are done with this example. This is the two-dimensional case. And the three-dimensional case really very similar. So I'm moving to the three-dimensional case. And again, it is the example. Mostly I took from the textbook. Somewhat it's two examples combined. And also I added a little more. Example 4.36a and 4.37. We are considering this function of three variables. And the first part, it is to find out the gradient at any point. And also I just want to make sure the gradient at any single point, there is a gradient, okay? So at a different point, there are different gradients. So first part, it's very general. We understand that the gradient, it is vector formed by partial derivatives. For a function of three variables, we got three partial derivatives. So it's a three-dimensional vector. That's what I meant. It's a three-dimensional vector. So I calculate partial derivative with respect to x from this line here. First term, that's 10x. Second term, that's negative 2y. And this is 0, 0, 0. One more term from here, that's plus 3z. Partial derivative with respect to x. Partial derivative with respect to y, this goes to 0. This is negative 2x. Then plus 2y minus 4z. These are the zeros. The derivative with respect, the derivative constant. Okay. So partial derivative with respect to y. Then similarly, partial derivative with respect to z. This is 0, 0, 0, minus 4y plus 2z plus 3x. The gradient at any point, and then the gradient at this particular point, you plug in this ordered triple for x, y, and z here. So this is the calculation I did. I plug in 1 for x, negative 2 for y, 3 for z. And I have to say it helped me double check with the number. I believe my number should be all right. If I see something wrong, I'll let you know. Or if you see something wrong, you let me know. Okay. And then part C, it is to find out the directional derivative in the direction of this vector. And so the solution for part C, first remember the directional derivative, it is always calculated as the gradient dot with the directional derivative for two-dimensional, three-dimensional, or later you may have higher dimensional things. The gradient, the directional derivative always can be calculated as the gradient dot with the unit vector, which is for the direction, Okay. So in part C, I'm talking about this example, the three-dimensional case, okay. Part C, we are having a direction in a three-dimensional vector, and we understand this will have to be a unit vector, right? So part C, first I calculate the unit vector. Given any vector, you multiply the reciprocal of the norm to the vector, that is the unit vector. The norm of 1i, negative 1i, 2j, and 2k, I think it is 3. It is 3. So accordingly, the unit vector in the same direction just turns to be negative 1/3, 2/3, and 2/3. That's the unit vector. And then the directional derivative at the single point, it is the gradient at the same point dot with the unit vector as the direction. So this is what I have, the gradient as we calculated in part A, and the direction, that's 25. I think I added them together, that's 25/7. Directional derivative, okay. And also, I hope you remember in the beginning of the semester, we talked about unit vectors. As we say, when we point in directions, we need to have a standard way to say a direction. And this also helps explain why we want to have a unit vector. Because in the same direction, when you calculate the dot product, if you don't have a unit vector, the derivative is not correct. And besides, if we know we could have different vectors pointing to the same direction, right? And then if you use any direction, any vector, the directional derivative would be different. That's not possible. So I hope this also explains why we spend time to work on unit vectors. In the calculation of the directional derivative, we do need to have a unit vector. And so this is the directional derivative I just calculated. Part D, the question is, at the same point, 1, negative 2, and 3, find the direction for which the directional derivative is a maximum. Did we say again, that's the gradient, right? So specifically, the direction, it is by the gradient, like such. I did not do anything. That's all about how you understand the question and how you understand the gradient. Gradient, it is a vector. It's pointing to a direction, and also it has a magnitude. So certainly the direction with the maximum rate of change, maximum derivative, certainly it is given by the gradient. And also part E, what is the maximum value of the directional derivative? Gradient again, gradient has a direction and a magnitude. The magnitude of the gradient, it just turns out to be the maximum value of the directional derivative. So this part I just calculated the magnitude of the gradient. And I'm going to save, well, for me, I say it's easy for me to say, try not to make any mistakes. And hopefully the arrangement is correct. And you may want to take a look how the number would look like, And as a quick hint, I just want you to know this is the maximum rate of change. So it got to be bigger than this 25/7. It's far bigger, right? 23 squared, 18 squared, 17 squared. I guess it will be, I don't know, more than 20. This is 25/7. So it makes sense, okay. That is the maximum rate of change. So I think this is all about section 4.6. I say there are two bigger things of section 4.6, gradient and the directional derivative. The gradient is a vector formed by partial derivatives. Two-dimensional vector, three-dimensional vector, function of two variables, function of three variables. Then the directional derivative can be found using the dot product of the gradient and the unit vector. And two more big things about the gradient. The direction of the gradient, it is pointing to the direction where the function has the maximum value of where the function has the maximum directional derivative. And also the magnitude of the gradient, it turns out to be exactly the maximum value of the directional derivative. Hey, thank you for watching. I'll see you next time.